8E, modeling geometric growth and decay. So previously with linear growth and decay, we're looking at examples where values will increase by the same amount or form a straight line. Geometric decay and growth is when we have increases or decreases that do not form a straight line. They're often sometimes referred to as exponential increases or exponential decreases. So let's consider two possible scenarios. I've got two numbers. One number is greater than one number is less than one. What happens? Well, if it's a number that is greater than 1, and I use this recurrence relation, as you can see here, Vn plus 1 is equal to A times by Vn, this will create geometric growth. If I've got some number b being less than 1, and I do the same thing, I multiply by Vn, what happens is that it will decrease, and this will be geometric decay. It's a fun fact, if the number was equal to 1, we'd get nothing. It would just mean that it would stay the same. Example 8E.1. Fill in the rule and sequence columns for the first four numbers, identify which one is geometric growth and which one is geometric decay, and plot a graph for these points. So I've got K0 is equal to 400, Kn plus 1 is equal to 0.75, and it says P, that should be a K, N. Well, it's a number less than 1 in front, so this is going to be decay. And so what's happening here, what it means is it's actually multiplying each term by 0.75. That's what that means. So what's the next numbers in the sequence? Well, it starts with 400. So that's the first one. And then what we need to do is times it by 0.75 each time. Now, I could use my CAS, or I could just go with a classic scientific calculator here, times 0.75, and that gets me 300. And then we'll times that by 0.75, and that gets me 225. And then we times that by 0.75, and then we get 168.75. So now we need to plot them. So there's my plot, and as you can see, it's starting to follow a non-straight line pattern. H0 is equal to 10, Hn plus 1 equals 3 times Hn. Since the number in front of the Hn is greater than 1, this is growth. And what does it mean? It means I'm multiplying each term by 3. So what are the numbers in the sequence? So the first one will be 10. The second one will be, of course, 10 times 3, which is 30, times another 3 again. That'll get me 90, times another 3 again, and that'll get me 270. So now we need to plot it. And if we follow those dots, you can see there I've made a curve. It is going in a very much a non-straight line pattern. So where is this used? This is used in the calculation and concepts of compound interest. All right, so imagine I borrowed some money. Yeah, I borrowed just a lump of money. And then we calculate a percentage of interest for the month that I have it. And I'll plop that on there. And now I've got a slightly bigger lump of money. The next month is then calculated from that new lump of money. And it gets slightly bigger. And then we put that interest in there, and then we calculate new interest and add it and get a slightly bigger lump. And then it grows and grows and grows and grows and like that. That is compound interest. So how do we calculate this? Well, we start with a principal, which is our V0. And then we have a capital R, which is the compound interest fee. And that equals to 1 plus little r over 100. And then that little r, of course, is an interest rate as a percentage. And I'm going to write here per compounding period. So this is the kinds of problems here really do rely on you knowing what the time periods are and keeping everything consistent. And the formula that we use for this is Vn plus 1 is equal to R times by Vn. Example 8e.2. A recurrence relation can be used to model a compound interest investment of $2,000 paying interest at the rate of 7.2% per annum. Write that recurrence relation. So, as per usual, I'll need to get my V0. So my initial or my principal value here, so it was $2,000. I've kept the sign in. You don't have to keep the sign in when you're running the recurrence relation. So in fact, I might just actually take that out for now. And so now we just need to write the formula. So we need to do RVN, but we need to work out what the R is. So the R is equal to 1 plus, and what's the rate? It says there per annum, and I don't think we've changed that. So it's just going to be 7.2 over 100. And this is equal to 1.072. So therefore, the recurrence relation will be 1.072 Vn. Use the recurrence relation to find the value of the investment after 1, 2, and 3 years. So what we need to do is we need to use that recurrence relation and do a substitution to find out what happens. So V0 is equal to 2,000. So V1 will be equal to, so again, we'll take the R value there, so 1.072 times by 2,000, and that's going to be equal to 2144. Then what we'll do is we'll do it again, 1.072 times by this new amount, 2144. That gets us equal to $2,298.37. And then the third year, 1.072 times by 2,298.37, which is equal to $2,463.85. You could also confirm to make sure this is correct by using the sequences option. So you'll notice here I've just put the interest rate, as you can see there, 1 plus 7.2 over 100 times by AN. I haven't even used the 1.072. I haven't even done that calculation. And now we've got all of the values that we need. So after the third year, as you can see there, 2463, 2298, you'll see it there, it says 0.4. Don't be fooled by that rounding. Look at the bottom. The bottom there says 2298.368. So we need dollars and cents. So you'll need to have it 2 decimal places every time. So it'll be 2298.37. Determine when the value of the investment will first exceed $2,500. So we want it. So when you say first exceed, so when will it be first more than 2,500? Well, since we've gone to the effort of making a sequence on the CAS, we may as well just use that. So when does it first reach over 2,500? It looks like after 4 years. Because the third year, it's 2,463 and 85 cents. So after 4 years. Do I need to write what the amount is? Nope. It just says determine when. So the when means I want a time period. D, write down the recurrence relation if $1,500 or $1,500 was invested at a compound interest rate of 6.0% per annum. So once again, we want the R, which is 1 plus, I should say, 6 over 100, and that's going to be equal to 1.06. And now I will write it like so. So V0, the initial was 1500. And then Vn plus 1 is equal to 1.06 times by Vn. It's not good enough just to write RVN as your final answer and solve it accordingly. You do need to actually put it in. So make sure you say V naught equals 1500, Vn plus 1 is equal to 1.06 times Vn. Reducing balance depreciation. So this is the opposite of a linear, of a geometric growth or the compound interest. This is when I'm actually paying back a loan, and most loans in real life operate in this way. We calculate it thusly. So the rule, or the recurrence relation, will always be Vn plus 1 equals RVn, where the principal is the same thing. It's the V naught, it's the initial amount. The only difference compared to the previous is that the R value is not 1 plus, but 1 minus little r over 100, where little r is the interest rate per compounding period. Let's have a look at an example. Example 8E.3. A new car was purchased for $36,000 in 2017. The car depreciates by 10% per annum. When you see per annum, that is of course meaning year. Annum from the same root as annual. Model the depreciation of the car as a recurrence relation. So I'm going to start by writing V naught is equal to the initial amount, which was 36,000. And then we need to write the rule. So we need to work out what the R value is. So R is equal to 1 minus the little r. So the rate, which is 10 over 100. And this is equal to 0.9. So my recurrence relation is 0.9 Vn. What is the value of the car in 2019? So again, I could keep substituting in, but honestly, let's use the sequences option because that will make this much more efficient. Grab my calculator here and we'll rewrite this equation. So instead of saying 1 plus 7.2, I'm going to do 1 minus, and then rewrite this to say 36,000. So now there's my equation. So you'll notice there I haven't bothered to use 0.9. I'm just substituting, as you can see. And now here are all of our installments. So we want 2019. So the initial amount was when V naught, that's 2017. V1 will be 2018. And then 2019 will be the next year after that, so V2. So this will be V2, which is equal to 29,160. Just making sure that I haven't done any rounding errors.